about Eris. Okay, welcome to the Eris video. Let's get to know more about this dwarf planet, so sit back and relax and enjoy this wonderful video as we get to know more about this special dwarf planet. Okay, so we're going to start by looking at the masses of these 5 dwarf planets. These are the recognized dwarf planets by the International Astronomical Union. So we're going to have the mass, which is the y-axis or the vertical axis. Then on the horizontal we're going to have the planets. So as you can see with the bars that have popped up there, we have the one which is in white for Eris, showing that it is greater in mass than the other dwarf planets in the solar system. These are the planets in the solar system. So the dwarf planets in the solar system, amongst them Eris is greater than the others, or bigger than the others in terms of mass. But in terms of volume, there was a debate on whether to call Eris larger than Pluto, because Pluto was considered the 9th planet, then Eris was considered the 10th planet. Then later on in 2006, after the redefinition of the term planet, these two were demoted from being planets and they became dwarf planets. Hence we have this category, which is enacted in resolution B6 of the International Astronomical Union. So we have Eris now being larger in terms of mass than Pluto, but it's smaller in terms of volume than Pluto. Therefore, it's called the decision now is we'll consider volume because of dimensions of the planet instead of the mass, to say it's bigger. So Pluto, because of the dimensions that are involved in volume, Pluto becomes bigger than the dwarf planet Eris. Quite fascinating, but yeah, that's basically the idea behind what we now call the dwarf planets. So those are the masses. We have Eris having the largest mass, and compared to the others, I didn't include a bar graph on volume. Could have done that, but maybe you can just do it yourself, since I gave you a lecture on representation of data in the statistics video. If you haven't watched it, please go and watch it. I'll try and insert a link for you, so it is easier for you to go and watch it. And then after that you can draw your own bar graph, as I've done here in this video. And this mass that you're saying, 16.6 times 10 to the power 21 kilograms, the mass of Eris, it was actually calculated after the discovery of Eris' single moon. Like Earth, Eris also has a single moon, and the name of the moon is Dysnomia. So after the discovery of Dysnomia, it became easier for scientists to calculate the mass of Eris, which is what you're now seeing here, represented by that white bar. So I think we're done with the masses. Let's move on to orbital period. I think with orbital period I've done justice in the previous videos to explain how we get t is equal to 2 pi multiplied by the square root of the same major axis cubed over the gravitational constant, the product of the gravitational constant and the mass of the sun. In that diagram there, which you are seeing with the sun and the dwarf planet Eris, it represents what we are trying to calculate here. It's only that it's in terms of time. So according to Kepler's third law, which states the squares of the orbital period of the planets are directly proportional to the cubes of the same major axis of their orbits, which is represented by that expression t squared over r cubed, in this case z cubed, is equal to 4 pi squared over gm. And then we get our expression, which is at the bottom there, encircled or inside that yellow boundary there. So now let us try and calculate the period using that expression. If you don't understand how to get that expression, you may need to visit the Make video, the Planet Saturn video, the Venus video. I think I also covered that. Mercury, I think I covered that as well. Just go and visit those videos, and you will get a better understanding of how to get that expression. So now let's move on to the calculation. So we begin by using the expression t is equal to 2 pi multiplied by square root of that z cubed over gm, and then we plug in our values. We know our same major axis. This time I'm not going to calculate it. I'm just going to give you it's 10.152 by 10 to the power of 12, which means it's tera. It's in terameters. That's why it's 10 to the power of 12 cubed. And then we have over the gravitational constant, which is that number we all know, and the mass of the sun, which is to the power of 30 there, by 10 to the power of 30 there. And then we get that 1.76399273 by 10 to the power of 10. Then we are going to divide, because we want to find the period t in earth years. That's the instruction at the top there. So we have to convert it to earth years. So in order to convert it to earth years, we have to divide by 60 seconds, 60 minutes, 24 hours, and 365 days in a year. So it's so that we convert to minutes, then we convert to hours, then we convert to the days, and then we convert to the years. So that's why we have to say 60 by 60 by 24 by 365. If we multiply that, we get the denominator. Then we divide into that number, and then we get 559 years. So it's approximately 559 years, but some sources like with the NASA from America, they have 557 years as their figure for the number of years for Eris. Well, we haven't gone to Eris so that we can experience that. It's more of estimation, so maybe there might be some slight errors in terms of collecting data, but even if there are those errors, it might not be true, because these values are just based on images that were taken by a certain team, which was led by an astrophysicist called or an astronomer called Mr. Brown. Mr. M. Brown is the one who managed to find out about this planet. They took images, found that it was in motion in the 3 frames that they took in some hours, and then they announced that they got to see the planet in around 2005, I think. So that's basically how we find the period. The period in terms of our calculation is 559 years just to go around the sun. While this Earth is taking 1 year to go around the sun, Eris takes 559 years to go around the sun. And also, if you look at the orbit of Eris and the orbit of the other planets and dwarf planets like Ceres and Pluto, they are very close to the sun. Eris is very, very far away. We talk of the scattered orbits, rather the scattered objects, which are far away from the sun, beyond the Kuiper belt of Neptune, of planet Neptune. So yeah, that's basically something that we are trying to look at here. How long does it take for Eris to go around the sun? It's actually 559 years, or 557, or 558, depending on the source you're using. But there might be a need to also find the accurate value so that we have a proper understanding of the relationship between our orbit around the sun and the orbit of Eris. But I think with these values we can clearly see that it takes a very long time just to go around the sun. So I think we understand there. Let's move on. Okay, now we move on to the surface gravity. So I think it was the make video. Make is one of the dwarf planets, as we saw in that bar graph. I think we put make there. If you look for that video, you'll find, or I'll put the link here in this video. You'll find that there's a part where I explained how you to interpret that diagram there, with the green line, which is the radius, and then the blue line is where the mass of Eris is localized, and the yellow dots outside there, I think in that case it was the white dots. Here it's yellow, so that yellow dot on the surface is getting to experience gravity from the center to where it is on the surface, hence we have that radius being used. So let's look at how we will calculate that gravity that it is feeling, that the yellow particle is feeling on the surface of Eris. So we first use Newton's law of universal gravitation. That is the law that we're going to be applying here, which is basically showing that the relationship between the masses, the product of the masses, which are m and m, as you see in that blue illustration there, where we are cancelling the m's there. You see there's a capital letter M and the small letter m in that expression, over r squared. So there's a relationship between those masses. the product of those masses, and the square of the radius, or the square of the separation of the masses. It can be the sun and another planet, there's a separation there. It can be a particle on the surface of a planet and the center of that planet, that's another separation, which is the radius, as we can see here. And when we say center of the planet, we are meaning inside the planet, like at the core of the inner core of the planet. Yes, that's the center, that's the center I'm talking about, not on the surface, as you can see. If you look at it there, you would think maybe it's going round the planet. No, it's cutting inside the planet. I couldn't find a image to insert there which shows the inside of that planet. So just imagine the line is cutting into the planet, not on the surface. So let's now look at how we find our G. So for G, we equate that expression gm m over r squared will be equal to mg. Mg is coming from ma. F is equal to ma, which is Newton's second law, which talks about the relationship between force and the acceleration. In this case, the acceleration due to gravity, which is g. So g would then be equal to gm over r squared. If we rearrange all those values there, or the terms there, it will become g is equal to capital G over capital G m over r squared. And that's basically those values there. So we have the mass. The m is the mass of Eris, not the mass of the sun. We were using the mass of the sun before. In this case, we're dealing with mass of Eris and the mass of that yellow dot on the surface of Eris. So it's the mass of Eris that then takes the greater mass symbol, which is the capital M, and then it's over the radius of Eris, which is that 1,163,000 meters squared. We then square that was r squared. Then we get our G, which is that, which is 0.82 meters per second squared, to two significant figures or two decimal places. And then the G of Earth is 9.81 meters per second squared. We're going to try and see the relationship between the gravity on Eris and the gravity on Earth. We want to see the effect, is which one is stronger, the gravity on Earth or the gravity on Eris. So what we're going to do, if you understand this, if you've watched the the statistics video. Some of these things, for you to understand, you need to have also looked at the statistics video. If you're not familiar with these mathematical expressions and terms and calculations. But basically, you're looking at the ratio of the gravity on Eris as to gravity on Earth. If you find even on Wikipedia, that's how they express the relationship between values of certain quantities and magnitudes of different planets compared to Earth. They do that calculation. So as you can see, it's that gravity over the other, and then we get that value 0.83 something. So you just use that figure, you multiply it by 9.81, and then you get the gravity, acceleration due to gravity on Eris. So that's basically how you do it. So it's 0.83588 compared to the gravity of Earth. So it's basically you take that value, multiply with the gravity of Earth, and then you get the gravity of Eris. The same, you can even convert it to a percentage by multiplying by 100. So you multiply that value 0.83588 whatever by 100, and then you get your 8.36% of the gravity of Earth. So it's like it's 8.36% of the gravity of Earth. But we're not saying that the gravity is from Earth. No, we're saying the value of the gravity on Earth is more than 90% in terms of its value compared to the gravity of Eris. Yes, it's very, very much great. So that's what we're trying to say here. I hope you have understood. So let's move on to the astronomical or geometric albedo. Okay, so what is albedo? It's basically a word which is derived, as you can see in the statement, note at the bottom right, that it is a word that was derived from a Latin word which means white or whiteness. So basically we are trying to look at how much light can be reflected by a planet. Not exactly its whiteness, but as you can see, white light is the one which is the spectrum, it contains all colors. So the words would suffice for us to use for such a term for reflection of light. So basically the geometric albedo, which some also call astronomical albedo, is basically the ratio between the light received and the light reflected by a planet. As you can see, when you are the observer there in that diagram, you have those distances there. So the light reflected is from Eris to the observer. It's coming from Eris to the observer. The observer is able to see how much light is reflected, but you have to consider the distance in which the light is going to travel from Eris to the observer. And the light from Eris is not the source of light. So our source of light has to be factored in, which is the sun in this case. So it's the sun gives the light, that's the source of the light, which means we need that distance between the sun and the object which is reflecting, the reflector, as you can see stated there. So basically that's what we are talking about. It's the ratio of the light received and the light reflected by that planet. So now we need those distances. Why do we need them? Because we need to calculate something called the absolute magnitude. Yes, it's a quantity that is needed in the calculation of that albedo, as we are going to see later on. It's represented by the letter H. That's the absolute magnitude. We have an apparent magnitude and other types of magnitude, but that absolute magnitude is the one that is calculated using these three distances that we have that are in that diagram, as you can see in the blue diagram there, with the blue lines and written in blue. So for this albedo we have parameters as stated in that definition. We have 0, which means pitch black, to 1, which means the perfect reflector. That's basically the range, or that's basically what I mean, the limits or parameters, whatever you want to call it. So we're trying to say our albedo values are going to be within that range from 0 to 1. So it's going to be in decimal form. 0 means it's complete darkness, pitch black. Then 1 means perfect reflector, it can reflect the light. And I think you have seen with the diagram of Eris that it's very, very bright. The surface is very bright. You're going to see that when you look at the environment of Eris in a few slides to come towards the end of this video. You're going to see that it's bright, and there's an explanation for that. So now let's try and calculate this albedo and see where in that range does the albedo of Eris fall. So we're expecting the albedo of Eris to be very close to 1 because it has a bright surface. So we are saying it reflects a lot of light, and therefore we're expecting that its albedo, its geometric albedo, is close to 1. So let's see. Okay, so where H is the absolute magnitude of Eris, which we talked about when we were talking about why we have those distances, why we need to consider those distances. It's the absolute magnitude of Eris, and D is the diameter of Eris in kilometers. Take note of that. It's the diameter of Eris in kilometers. We have to specify that it's in kilometers because in most of our calculations we use what we call standard international units. The units that are used in calculations have to be standardized so that we get the same values, so that we get to understand and interpret the values that we get and the calculations that we're doing. So in this case we are going to be using kilometers, so we're not going to be using meters. The standard for distances according to the SI units, it is meters, but here we are being told we're supposed to use the kilometers for this kind of a calculation. So let's find A, which is the geometric albedo. So the expression is A is equal to 1329 by 10 to the power of negative h over 5. That's the power of 10 over the diameter, and then that entire part will be squared. That entire expression will be squared. So that's how we find the geometric albedo. So when we put in the values, our h will be negative 1.21. That is the one for Eris, the absolute magnitude for Eris. And take note that negative 1.21 over 5 is negated again. So we have that bracket, that thinner bracket there, and the negative sign at the left there. Yes, to show what we mean by negative h over 5, which is the negative of the absolute magnitude over 5. And then the denominator, which is d, is 2326 kilometers. Take note in kilometers. And then you square that, and then you get your geometric albedo, which is around 0.995, correct to 3 significant figures. So we are pretty sure that Eris reflects almost all light. It's a perfect reflector or rather it's very close, very close to a perfect reflector. 0.995. Definitely, we can even call it a perfect reflector, because if we round off to the nearest whole number, it's 1. But basically what we're trying to say is this Eris has a white surface which enables it to reflect the white light from the sun. Yes, I know some people are going to be shocked, but the sun is actually white, it's not yellow. I also was shocked when I found out, the first time I found out that the sun was white. It wouldn't make sense for us to be seeing all colors clearly from outside if the sun was yellow. It has to be white. If you look at it, it's actually white. But I'm not encouraging you to look at the sun directly. Make sure you're wearing something. What makes it look yellow, I'm being serious, but yeah, you hurt your eyes. What makes it look yellow probably is the diffraction and the attenuation of the light as it is passing through certain layers in the atmosphere. So probably that's why it appears to be yellowish, but the sun is actually white. So if Eris has a white surface, it means that it's going to reflect all the colors in the spectrum of light towards the observer, and that's what we may see as a perfect reflector as well. It's reflecting all the colors. None of it is absorbed or whatever. So that's basically what we look at when we look at albedo. It's basically how much of reflection can be done by that object after receiving light from a source, in this case being the sun. So let's now move on to the eccentricity. Alright, so if you read the note there in white, eccentricity is the measure of the extent or degree of deviation of a body's orbit from its circularity, or the degree of losing its shape of a perfect circle, thus creating an ellipse. That's basically eccentricity. If you continue, you see that eccentricity as 0 means that it's a perfect circle. If it deviates from that 0, it means it's now starting to lose its circularity, and therefore it becomes an oval shape, more of an oval shape, as you can see with the blue oval that you are seeing there in that diagram. It means that its eccentricity is greater than 0, and that diagram is better than the other diagrams we looked at. The other diagrams were supposed to be circular in shape, almost perfect circles. As you're going to see in one of the slides that are going to come, the next slide that's going to come, you're going to see how the orbits look like for, I think, Pluto, Neptune, and Eris. You're going to see all those, and you get to compare the shapes of the orbits, and I think that will make you understand this note and understand this phenomenon of eccentricity. So eccentricity is epsilon is equal to that expression where A is the aphelion and P is the perihelion. So that's why we have the aphelion and the perihelion there. So we then plug in the values for the aphelion and the perihelion. Basically the aphelion and the perihelion, I think we already know. If you don't know, you might need to visit the previous videos. It's best explained there, where the aphelion is basically the distance where Eris will be furthest from the sun, and the perihelion is, we also call that the abscess, and then the periapsis is also called the perihelion in terms of planets, which is basically the shortest distance when or the distance when Eris is not far from the sun, the shortest distance when Eris is not so far from the sun. Those are the values to put there. Those ones are in astronomical units. You can use the ones in meters. The choice is yours. The units will cancel out. That's why we can use any of the units. We don't need to follow the rules of calculations using the SI units, because those will cancel out as a fraction. They have the same units. So we'll say 1 minus that. But if we get 1, if we are to get 1 from that fraction as our answer, it means that the fraction has the aphelion and the perihelion having the same values, which means the orbit of that planet will be circular in shape, perfect circle, meaning that we have radius. We don't have aphelion and perihelion, we just have a radius of the orbit. But I don't think we have such a case in the solar system. If there is such, maybe I might need to look at it, but I haven't found any case. Most of the planets, if you look at, I think, the Mercury video, we showed the eccentricities in terms of the bar graph, and you can see that they are not equal to 0. None of them is equal to 0. So if there is an orbit which is perfect circle in the solar system, just hit us in the comment section, and we'll look at it. If you then plug in the values of the aphelion and the perihelion for Eris, which are the 97.457 over 38.271, you then get 0.43606 is your eccentricity. which means it's greater than 0, meaning that the shape of the orbit is oval in shape. You'll get to see that it's 0.4. But for the 8 planets in the solar system, the greatest eccentricity is around 0.21, and that is the eccentricity for Mercury, the smallest planet in the solar system. So that means the eccentricity of Eris is more than twice than the eccentricity of Mercury, as of which Mercury has the greatest eccentricity than all the other 7 planets in the solar system. Quite fascinating. You're going to see that in the diagram that's following after this calculation. So we will then express it to 3 significant figures, as we always do, for accuracy. And I think we have understood these calculations. If you haven't understood, just revisit them or go and watch the videos that I've recommended throughout, so you get to understand these calculations. As for the calculation section, as usual, cheers. I think I'm done. We will meet next time when we look at another video. I'm hoping that we'll be looking at another planet, probably Jupiter, next. So until then, cheers. More about Eris. Now, Eris.